Hey everybody, Dr. Retzik here. This is our second video in chapter 16, and it's the intro to 16.2, which is all about vector fields. Let's get started. So I've put an array of black arrows on our iPad screen, and depending on where you are, the arrow points in a certain direction and has a certain length. So this one here, emanating from that dot, points pretty much straight to the right and is of medium length. This one here, emanating from that dot, points up and to the right and is a bit shorter. This one here, located at this dot, that one points down and to the left and is a bit longer. So depending on your location on the iPad screen, you will find an arrow of a certain length and direction. And this is an example of what's called a vector field. And that's really all it is. A vector field is a function that assigns to each point in space some vector at that point. Now, you can imagine it, if you like, as maybe like that's the wind velocities, like on some kind of a weather map, or maybe it's some sort of magnetic force field or something in physics class. But really, at its heart, it's just a function that assigns to each point in space some arrow. Okay, we're going to be interested in studying these vector fields, and in particular, their behavior along curves. So now I want to superimpose some curves on this picture. So I'm going to start with a purple curve, like this, say. So that curve starts here and ends here, and we can call that curve C1. Now, it's got a certain direction to it. Remember, there's a starting point and an ending point to this curve, so it's traced out more or less left to rightish. And it seems to be going kind of in the same direction as the vector field, vaguely, kind of along the black arrows. On the other hand, you could have this orange curve, say like this. So maybe this is, you're going out for a jog in the neighborhood and you're going to make a loop. You're going to leave your house, you're going to go run around, and you're going to arrive back at your house. And some of the time the wind is with you, and some of the time you're sort of dead against the wind, but on the whole, it kind of balanced out in this picture, and you have some sort of total sense of what effect the wind had on your run. Okay, and then there's this curve, so let's call that one C2. And then there's this curve, say in blue, C3, like this. So here's C3. It's traced out this way. Now, if that had been your run, you would come home complaining because you had been running effectively into a headwind the entire time. So depending on the path you take through a vector field, you sense different effects that the black arrows in the vector field have on your path. Okay, so let's focus for a moment on, say, C1, the purple path. So I'm going to draw that a little more cleanly off of the original picture, extract it from the vector field, and see C1 like this. So here's C1 in purple. So there's the ending point there. Here's the starting point here, and it's being traced out in this direction. Okay, now at a given spot on that curve C1, there will be a black arrow. Okay, so let's put the black arrow in, say, here. At this spot on the curve, there's a black arrow, and let's say it goes like that. Okay, now, also at that spot on the curve, there is an actual tangent vector to the curve, say like this, and let's just assume that that's the unit tangent vector in a Calc 3 sense. So you can take the derivative of your curve that produces a tangent vector, divide by its own length, and you get what's called the unit tangent vector. And I think back in the day, in Calc 3, we called that big T. Okay. So there's some question as to, well, how much of that black arrow is in the direction of the curve, and how much of that black arrow is irrelevant as far as one's path along C1. So you can kind of think of that black arrow as being broken into two pieces, two components. There's this piece in orange. That's the component of the black arrow in the direction of the unit tangent vector. And then there's this piece in green, which is the part of the black arrow completely perpendicular to the unit tangent vector and therefore not at all in the direction of the curve itself. All right, so let's give that black arrow a name at this point. Can we call that black arrow capital F? And we're going to make it look like a vector because, again, the vector field is just some function, so let's name it capital F, but let's use that vector notation to reinforce that at each point, capital F produces a vector at that point. Okay, so we're interested in the part of capital F in the direction of big T. So what if we wanted to find this length here? If we were interested in that length, well, that's the projection of big F onto big T. That's the projection of black arrow onto purple arrow. And if you remember, like if you called this theta, if you wanted, then that distance right there, that's magnitude F cos theta. Okay, so the amount of the black arrow in the direction of the purple arrow is just magnitude F cos theta. Now check this out. Magnitude F cos theta is equal to magnitude F magnitude T cos theta. And that's just because T is a unit vector, so magnitude T is 1. But when we put it in there like that, this is nothing other than big F dot big T in a Calc 3 sense, good old dot product. So the key thing about this picture is that the amount of the black arrow in the direction of the purple arrow is nothing other than black dot purple. That's it. Okay, so we're going to define the line integral of the vector field along the curve C1 in the following way. You're going to figure out what f dot t is at each spot and use that as your function to do a normal line integral with, like in a 16.1 sense. So right here, this guy is the f from 16.1. So you're just doing the line integral over the curve C1 of f ds, where f happens to be big F dot big T. So that means the same thing it's always meant, just in a 16.1 sense. Now, if you actually put in what big T is, though, how did we get that unit tangent vector back in the day? Big T is just the tangent vector divided by its own length. And you remember big ds, is just speed times time as our little mnemonic device to remember that ds is just magnitude r prime times dt. That's a rate times a time, and that gives you a little bit of distance along the curve, which we called ds. So in the end, all you really have to do is take f, dot it with r prime, and integrate all that with respect to t. So if this is t equals a, and this is t equals b, then the limits on that integral are a to b, and you have nothing other than this, integral a to b f dot r prime of t dt. So in practice, that's how you're going to compute it. And not only that, that's the motivation behind this notation. So the notation they use for the line integral of a vector field along a curve parametrized by some function r is this. This is just pixels. They write it like this. F dot dr. So that symbol right there, those pixels, that's the line integral of the vector field along the curve C1. And the way you compute it is you turn everything into t's, and you actually do that integral. Okay, let's put this into practice. Your suggested problems initially are just going to ask you to compute some line integrals of vector fields over curves. So let's say we had this. So let's get a nice clean sheet. And let's say we had this vector field. Let's have this be in 3D space. So f at the point x, y, z is the vector z x, y, y squared. Okay, so if you stand at the point x, y, z, that's the black vector at that point. Okay, and r of t. Okay, so r of t, this is the curve. This is the purple curve. All right, so let's just make something up. So r of t is t root t squared, let's say. Okay. So, oh, and we better say like what t values. So let's say t is going to go 1 to 3. So that traces out some sort of curve in 3D space. Okay. Now let's say you wanted to compute this. So they want you to do the line integral of that vector field along that curve C. Okay. All right, well, first of all, C is traced out as t goes from 1 to 3. And now we're consulting this part of the definition of the line integral. So we're going to do f dot r prime of t, all done dt. Okay, so let's put r prime in right here. So that's r. So r prime is the vector 1 over 2 root t, 2t. Okay, and then we have to dot that with the vector field. Now this looks weird at first because your vector field, look. It's got x's, y's, and z's in it, but you're trying to turn all of this into something with t's. But here's the key. On the curve, this is your x coordinate, this is your y coordinate, and this is your z coordinate. So all you have to do is, everywhere you see an x, just put a t. And everywhere you see a y, just put a root t. And everywhere you see a z, put a t squared. So the integral comes down to this. All right, here's big F, parametrized by t. So first coordinate is z, and the role of z is being played by t squared. Next coordinate is x, y, and the roles of x and y are being played by t and root t respectively. Last coordinate is y squared. The role of y is being played by root t. So that's F, evaluated at spots on the curve, parametrized by t. Now you got to dot that with r prime. 1 over 2 root t, 2t, and you got to integrate the thing, dt. Okay, we're good with dot products. Let's just do it out. So that's t times 1 plus t root t times 1 over 2 root t. Root t's cancel, so plus t over 2 plus t times 2t, all done dt. And now it's just a normal integral from there. Depending on the parametrization of the curve and the vector field, you could end up with something gnarly to integrate with t's in it, or you could end up with something straightforward like we did here. The point is this: if you're trying to compute the line integral of a vector field along a curve, you're trying to capture just the parts of the black arrows that point along the curve. And that capturing is done by dot product. Okay, go practice. Come to class with questions. We will start to see applications of line integrals of vector fields emerge here in chapter 16. This is some of the most applicable and powerful calc stuff you're going to learn moving into your science and engineering classes. All right, see you next time.